In this video, we're going to build up the toolset of game theory. We'll start with static games, where individuals make decisions, strategic decisions, simultaneously without observing what the others have done. We'll introduce the idea of normal form games, which is just a matrix, typically in 2 dimensions. Talk about dominant strategies, best response functions. We'll introduce the idea of a Nash equilibrium, which is a relatively broad concept that allows us to talk about equilibrium in a relatively broad range of contexts. And we'll talk about different definitions for restrictions on the definition of Nash equilibrium. We'll walk through a very particular social dilemma, which you may have seen before, the prisoner's dilemma, and talk about how to solve the prisoner's dilemma using pure strategies and mixed strategies. We'll talk about cases when we have multiple equilibria, and we'll introduce the idea of mixed strategies in the social dilemma and in a similar but strategically very different type of game with multiple equilibria. Then when we talk about dynamic games, we're really talking about repeated and sequential games. We won't touch on these too deeply. We will introduce the idea of a game tree, which will allow us to capture the strategic elements of repeated and sequential games in a graph. And last but not least, we will refine our notion of Nash equilibria using what we call subgame perfect Nash equilibria, which is a subset of the set of Nash equilibrium. Okay, so that's where we're going. But as a sort of a general step back to sort of view the scene we're setting up for ourselves, up until this point in economics, we've dealt with environments where I don't need to know the specific decision the others in my environment have made. When we looked at perfectly competitive markets, it didn't end up mattering. When a firm chose their quantity, they were facing a perfectly horizontal demand curve. They were price takers, and so the decisions of the others in the market didn't matter. Similarly, when we dealt with monopoly and monopsony, individuals in the market weren't interacting directly with each other. They were mediated through the market. And we only had one buyer and one seller. So the decisions of any others in the market had no effect on their optimal choice. But these cases are not universal. There are many environments, particularly what we'll get to in the next video, oligopoly, where my best decision depends on what you are planning on doing, and your best decision depends on what I'm planning on doing. And this is where having the set of tools that game theory allows us makes analyzing more complex environments much clearer. So that's where we're going. To do this, we have to set up a couple definitions here. The first is a game, which is just an interaction between players using strategies. And a strategy is an action plan that specifies the action the player makes conditional on every possible contingency. So this basically means I have to look into the future. I have to imagine everything possible that can happen and write down a plan for each of those possible contingencies. And that's a strategy. An action is simply just a choice in the game. So this is defined by the game. So the game gives me some set of actions that I can take, and a strategy just is me writing down which actions I plan on taking at every particular point in the game. A payoff is the benefit the player receives. And the payoff function basically tells me the payoff at every possible outcome of the game. And defining the payoff this way is really convenient. Essentially, we're saying there are a couple ways of thinking about this. That players are maximizing their payoffs. And when we say payoffs, we're essentially just saying that the action is the solution to the payoff. So I look out in the world and I see individuals making choices. If I want to know what the payoff is, I simply I know that the action they're taking solves their payoff maximization problem. So that's one way of looking at it. The other is just to say that the payoffs are the thing the players are aiming to maximize. Okay, so in this class, we're really only going to deal with complete information, which is essentially just where everything about the game is common knowledge, information that's available to all players. So you know the structure of the game, you know the payoffs, and everything is known to all players. So I know that you know that I know everything. Later on, we if you go on to study more game theory, we relax this assumption, which makes the models much more complicated and much more realistic, and if you enjoy it, it makes it much more fun. So here, we're starting with static games, which the way we define a static game is just that each player acts once and acts simultaneously. So everyone's making choices at the same time and makes only one choice. We'll talk about dynamic games later on in this video. So to sort of set up the idea of a game, we typically begin with what we call a normal form representation of the game. It sort of gives us the simplest view of what's going on in the game. So we set up this payoff matrix. We'll call this game 1. We'll deal with 3 types of games in this video. You may have seen this before, and in fact you probably have in your intro micro class. On the row side, we have what we call row player, very creative, and we have 2 actions for row player. We have up and we have down. For column player, we have 2 actions again. We have left and we have right. So first, let's talk about how to read this payoff matrix. If row player chooses U and column player chooses L, then row player receives a payoff of 1 and column player receives a payoff of 1. If row player chooses down and column player chooses left, row player receives 0 and column player receives 2. And we can go through all of the different permutations of this. But that's essentially how you read it. You take the strategy and you intersect it with the strategy of the rival. Okay. So here's where it becomes useful to have some definitions around strategies. So first, we have what we call the dominant strategy, which is simply just a strategy that gives me a higher payoff than any other strategy I have, no matter what the rival is doing. So it turns out there isn't a guarantee that a player in a game has a dominant strategy, but for this game there is. So let's walk through this. So first, maybe we'll just start off by showing what the dominant strategy is. So first, the dominant strategy here is U for the row player. So when I look at U versus D, if the column player is choosing L, which one of these two is better for me? Is it U or is it D? Well, if I choose U, I get 1. If I choose D, I get 0. So U is my preferred option. But what if column player chose R? Which is better for me, U or D? Well, I look at 2 and I look at 1, and clearly 2 is better. So I'm going to choose U again. So in both of these cases, U was the preferred action. So that's what we call a dominant strategy. And we can also look at this for column player. See that L is the dominant strategy. No matter what row player is doing, column player should choose L. Okay. So we can walk through, like we just did, showing the dominant strategies for each player. But we aren't guaranteed that there is a dominant strategy. So to give us a better idea of what each player should choose, we have what we call a best response. A best response is just a strategy that maximizes a player's payoff given their beliefs about what the rivals are doing. So let's make this more formal. So essentially we're just saying, given what the other is doing, what's best for me? So what we can do here is walk through each of the possible choices of column player and write down, conditional on what they're doing, what should we do? Okay, and we, in this case, is row player. And the way we're going to do this is just by circling, or putting a box around row players' payoffs. Okay, so if column player is choosing L, we've already shown that row player should choose U. So let's circle the payoff associated with L and U. And if column player is choosing R, U is the better strategy. So let's box the payoff associated with U and R. Okay. So that is our best response function, which is U and U, or L and R. And we could write this down for column player as well. But here it turns out, you've probably already noticed that when there is a dominant strategy, it's also a best response. But a best response isn't necessarily a dominant strategy, even though a dominant strategy is a best response. Okay, so we know that a best response is a more general principle than a dominant strategy. The next idea is what we call a Nash equilibrium, which is essentially every player playing a best response. Essentially, we're just intersecting our best response functions with our rivals. More formally, a Nash equilibrium is a set of strategies where no player can achieve a higher payoff by choosing a different strategy if everyone's using these strategies. Essentially, that's what a best response tells us. It's the best choice given what everyone else is doing. So to do this, before we go through and actually write this down for the Prisoner's Dilemma game, let's another way of thinking about the Nash equilibrium is a place, a set of strategies, a place in the game where no player wants to change their strategy unilaterally, what we call a unilateral deviation. Me changing on my own. And the thing is here that a Nash equilibrium in this way is so central to everything we do in economics that the main models we've discussed so far in this class, actually the solutions we've worked through are Nash equilibrium. We haven't really defined them exactly in these terms, but that's exactly what they're doing. We're saying, let's make sure the strategy is the best given what everyone else is doing. But it turns out in most contexts that we've dealt with so far, in fact, every context we've dealt with so far, it doesn't matter what the rival is doing. We know what our best response function is, and we know that our optimization doesn't depend on others' actions. Okay, so before I tell you what the Nash equilibrium is in this game, let's find the best response function for the column player. We've already shown that the dominant strategy is L, but let's write this down more formally, and we'll check unilateral deviations afterwards. Okay, so let's say row player is choosing U. Column player is choosing between 0 and 1. 1 is better, so column player chooses L. When row player chooses D, column player has a choice between 2 and 1. Since 2 is better, column player chooses L. So here, column player's best response function is L in every case, which is a dominant strategy. Okay. So when we've intersected the best response functions of row player and column player, we found that they're both the cell where they intersect is at UL. UL. And this, by definition, is a Nash. So let's, one definition for a Nash equilibrium is when the best response functions intersect. Another way of thinking about a Nash equilibrium is using unilateral deviations. So if we're in the Nash equilibrium, column player is choosing L. Is it good for me as row player to switch from switch from U to D? Well, no, because I would get a payoff of 0 instead of 1. So I'm going to stick with my Nash equilibrium, my best response function. And we could perform the same exercise for column player. We say row player is choosing U. Should I switch from L to R? Well, I would switch from getting 1 to getting 0. So no, I should stay with L. Okay, so this is indeed a Nash equilibrium. Okay. So we have a Nash equilibrium of U and L, which generates a payoff of 1 and 1. Okay, so here we're not necessarily saying that this is the best case for society. Here we're just saying it's the Nash equilibrium. And you could make this more stark if you wanted to. This is sort of a weak version of the prisoner's dilemma. We could make this 2 and 2. And here this, we could even make this 2.1 and 2.1. And nothing about this game would change. U is still the dominant strategy, and U is the best response function for row player. Column player, their dominant strategy is still L, and their best response function is still L. But it turns out the socially efficient set of strategies is this pink one, because it sums to 4, which is greater than everything else, but it's still not a Nash equilibrium. So the Nash equilibrium doesn't necessarily give us the best outcome for society. It just tells us what the equilibrium is, where no one in the game wants to unilaterally deviate. Okay, so let's look at another game. So game 2. So here, let's do this same exercise where we draw a red box around each payoff that corresponds to the best response. And when we've boxed both payoffs corresponding to both players' best responses, we know it's a Nash equilibrium. So let's go ahead and do this. So for row, let's say row chooses U. For the column player, they're given a choice between L and R. 1 is better than 0, so they choose 1. They choose R, getting a payoff of 1. If row player chooses D, column player is choosing between 0 and -1, so they choose L, giving them a payoff of 0. Okay, so that's for column player. Let's perform the same exercise for row player. Let's say column player chooses L. Row player is choosing between 0 and 1, preferring 1, so they choose D. If column player chooses R, row player is choosing between 0 and -1, and 0 is better, so they choose U. Okay, so we have 2 Nash equilibrium. at UR and DL. So these two here. And it turns out there's no dominant strategies. The best response depends on what the other player is doing. So at this point here, you might wonder, how do we pick which of these two equilibrium? And we don't, in game theory, we don't, at least at this level, have an answer to that question. We can't really arbitrate it with the tools we have available to us. There are some attempted solutions to equilibrium selection. Is the subfield equilibrium. I actually have a paper dealing with some of this, where the question is, when we are facing multiple equilibrium with maybe different levels of social efficiency, how do we arrive at in equilibrium? How do we choose? And it's a question that we can't quite approach with the tools in this class, but it's a good question. Okay, so what we've done here is we said there are multiple equilibrium. What we need to do next is make our game broader. So what we've done so far is we've said we're only going to allow players to choose actions. So you can either choose U or choose D. But what if row player decides to bring a coin? What if row player flips the coin? If it's heads, they choose up. If it's tails, they choose down. This is what we call a mixed strategy, where instead of choosing a single action for each possible contingency of the game, which is a pure strategy, what if instead of picking actions for every possible contingency, we pick which die to use to determine which action to play? So instead of choosing actions, we're choosing some randomization device to tell us which action to play. This introduces some difficulty for column player, right? If I bring a die, they don't know which action I'm choosing. And there's randomness. There's no determined action for me to play. This randomization is what we call mixed strategies. Essentially, this is a choice of probabilities which are assigned to each action. So we're placing probabilities on each potential choice we're making. Excuse me, each potential action. So, viewed from the perspective of mixed strategies, and we'll get into why mixed strategies really matter. From the perspective of mixed strategies, a pure strategy is just a probability distribution where an action has a probability of 1, or we choose it 100% of the time. It's like a coin that we toss where both sides are heads. It's still a mixed strategy. It's just a sort of degenerate probability distribution. Okay, so all pure strategies are mixed strategies, where the action is chosen with certainty. Okay, so let's let's refer back to our game 2. And let's say we actually used a coin toss. So let's say column player brings a coin and flips it. If it's heads, they choose left, and if it's tails, they choose right. And let's say the coin is fair, so the probabilities are 1/2. So row player, when deciding to choose U or D, will use these probabilities somehow to form their best response function. So to do this, we set up what we call an expected payoff, which is the probability of columns strategies times the payoff given to that strategy. And then we just add up all the strategies. So it's just the probability. So the notation here is we have our strategy sigma, which is the coin toss over L and R. Sigma, conditional on sigma, row player's expected payoff for choosing U is the probability that column player will choose L times the payoff for row player when U and L are chosen. And then we do the same thing for all the other strategies. So in this case, it's just, there are 2 of them. We have 1/2 times the payoff associated with choosing U and R. Okay, so to make this more concrete here, let's plug in some numbers. So we have 1/2 and 1/2 are the probabilities. The payoff to row player of choosing U and L, choosing U and L gives row player a payoff of 0. And if column player ends up choosing R, then row player also receives the payoff of 0. So let's plug these numbers into our payoff equation here. So we have the payoff, payoff function. We have 1/2 times 0 plus 1/2 times 0 gives us 0. Okay, so 0. The answer here is 0. It's a little bit straightforward and boring. So let's make this a little more interesting. The next thing we'll do is introduce the idea of a mixed strategy equilibrium, which is essentially just an extension of our original Nash equilibrium concept into the space of mixed strategies. And to do this, we have to look for this indifference point, where row player chooses their mixed strategy such that the column player is indifferent between choosing L and R. So row player is aiming to make column player indifferent between L and R. And you can think about what would need to be true, what would happen if this wasn't true. Let's say row player chose a strategy that made column player prefer L. If this were true, column player would just always choose L. And if column player was always choosing L, then row player would choose the best response to L. So the only point this isn't true is when row player makes column player indifferent between their two actions. So a mixed strategy happens when both players are making the other indifferent. Okay, so let's walk through this math. So the terminology here is that row player is choosing their strategy sigma sub r such that the payoff for column player, conditional on row player choosing the action, if column player chooses L, their payoff is the same as if they choose R. So we can use our definitions here from up above. The way we set this up, it's the probability of the event happening, the coin toss landing heads, times the payoff when that event happens. And then we add it up, we sum over all the probabilities and events. Okay, so let's do this here. So the first step is to define the probabilities. So we're saying P sub U is the probability that row player ends up choosing the action U. And then we multiply that probability times the payoff to the column player if they choose L, given this event. So it's the probability of U, the payoff of L and U. Then we just do this for all of the possible outcomes. So probability of D times the payoff to the column player, choosing L and choosing D. And then on the other side of the equality, we have the probability of U again. So that's the same probability as over here, times the payoff for the column player of R and U, plus the probability of the event D happening, row player choosing D, times the payoff to the column player, given players choosing R and D. Okay. So we've set this all up in terms of the column players' payoffs. But what we're doing is solving for the row players' mixed strategy, which is a probability distribution. Because what the row player is doing is trying to make the column player indifferent. So we need this equation to tell us indifference for the column player. Okay. It's important to sort of remember that point, that we're row player is making column player indifferent. So to find row player's probabilities, we need to look at the column player's payoffs. Okay. So when we plug in our numbers here, we have 0, 0, 1, and -1. And that's just coming from game 2. 0, 0, 1, and -1. Okay. So when we simplify this, we obviously have 0 on the left-hand side. Then we have PU minus PD, which means they're set equal to each other. And because we need the probabilities to add to 1, so PU plus PD, we then have that each of them is equal to 1/2. So this is equal to 1/2. Okay. So that tells us Rho players' mixed strategy Nash equilibrium strategy. This isn't the equilibrium. For the equilibrium, we need to realize that because the game is symmetric, we've already solved for column player, which is 1/2 and 1/2. And this is the mixed strategy Nash equilibrium, which is sigma R, sigma C. That's the mixed strategy Nash equilibrium. Okay, so both players are flipping a coin to choose their action. And because of this, both players are indifferent between the two actions. Okay. And just a little side note here that because a pure strategy is a mixed strategy, pure strategies are also, pure strategy Nash equilibria are also mixed strategy Nash equilibria. So we've broadened the scope of Nash equilibria by allowing players to mix over their strategies. Okay. The reason we've done all this is because not every game has a pure strategy Nash equilibria. But one of the big results in game theory, especially early on, was proven by John Nash. This really famous paper. It was about, I think it was under a page long. It's famously short. Proving that all games have at least one mixed strategy Nash equilibria. So even though we don't always have pure strategy Nash equilibria, we always have a mixed strategy Nash equilibrium. Okay. So great. We have mixed strategy Nash equilibria. What we will do next is extend our definition of the game into more complex environments. So far we've looked at static games where there's a single action which is taken simultaneously by everyone. But of course we don't have to always look at this type of game. We can look at dynamic games where players play in sequence or repeatedly. But the way we analyze these types of games, because the games are more complex, normal form just isn't going to work for us. We have to be a little more kind of clever. So the tool we have at hand is what we call a game tree, sometimes called the extensive form. Okay, so what we do is represent decisions with nodes or points, and we represent actions as lines or branches coming out of these nodes or points. This is essentially identical to a graph from graph theory. Okay, so here let's set up another game. This is our game 3, and this is a sequential game. So player 1 moves first, followed by player 2. So player 1 is choosing between U, M, or D, so up, middle, or down, and player 2 is choosing between A, B, C, D, E, F, G, H, I. And our payoff function is telling us what the payoffs are for every possible outcome of this game. Okay. So the question here is, can we find a Nash equilibrium? And how would we do it? So maybe think about that just a second. Our last tools might give us some help here, but the fact that we're in a sequential world makes this problem sort of look a little different. So what if we used the fact that there's an end to this game? There's a tool called backward induction, and we're going to rely on this pretty heavily for sequential games, for dynamic games like this. So what we're going to do is introduce what we call a refinement to Nash equilibrium. We call it a subgame perfect Nash equilibrium. What you can realize is that there are subgames within this game where, conditional on reaching any particular point, player 2 is making a choice. So we can sort of cut the game into subgames. So each of these points broken off gives us a subgame. In our static games we've been dealing with, there was only one subgame, which was the entire game. So the game itself is a subgame. But we also have 3 additional subgames. What subgame perfect Nash equilibrium requires is that at every subgame, there's a Nash equilibrium. That every player is optimizing at every particular node. Okay, so this gives us a little more traction, but we need one more concept, backward induction. So backward induction basically tells us that we start at the end of the game and we look at the last move and we define the best response at the last move. So let's go back up. So what we're going to do is eliminate, for player 2, in every subgame that player 2 is choosing at the end of the game. So specifically these 3 games, these 3 subgames, 1, 2, and 3. We're going to eliminate all of the actions that are not a best response. So for player 2, A and C, we'll cross these out. A and C are not optimal. They give a payoff of 1, where B gives a payoff of 2. So if P1 chooses U, P2 should choose B. So let's do the same thing for the other 2 subgames we're looking at, 2 and 3. So if we end up at subgame 2, we can cross off D and F. E gives the highest path, and for subgame 3, we can cross off H and I. Okay. So this is clarifying. Because if you are player 1 and you know player 2 will choose B if you choose U, and we'll choose E if you choose M, and we'll choose G if you choose D, then you could just compare each of these 3 outcomes and decide which one is better. So we reduced the complexity of this problem using backward induction and subgame perfect Nash. Okay, so let's clean this up and write down what P1 will do. Okay, so P1 is looking at 1, 2, or 3. So 3 is the best, which means we cross out U and M, which means this path to this path is the subgame perfect Nash equilibrium. And we solved it using backward induction. Okay, and just a few last points here before we close out. A subgame perfect Nash equilibrium is a Nash equilibrium. We looked at static games in the past, which only have one subgame. So every Nash equilibrium in those games is also a subgame perfect Nash equilibrium. And we've solved for a subgame perfect using backward induction, where we sort of use the fact that we can easily solve the last move, to then work our way from back to forward, from back to front, to give us our solution. Okay, and then we went through and did this for this sequential game. Okay, in the next video, we're going to introduce oligopoly, where we have two firms competing in a market, and their best decisions depend on the decisions of the other firm. And the only way we can solve this is using the tools of game theory.